what we should do is pKa1 add pKa3 and divide it by 2. Now what the pK3 comes out? Because aspartic acids, glutamic acids, they are all side chain is charged. So that's why they have a pK3 value. This is a fixed value in the table. Now if it's a base, what we should do is pKa2 value add the pKa3 value and divide it by 2. This comes out with base. Okay? So if you want to do a practice question, a very simple practice question, we can do a question here. If it's alanine, I have aspartic acids. Aspartic acids. I have arginine. Okay, I want to do it's a pKa1, pKa2, and pKa3. So let's see the value. If alanine, we have 2.34. This is 9.69, and this guy 1.88, 9.60, 3.65. The last one is 2.17, 9.04, and the 12.48. So how you do the calculation? For alanine, it's simple. The final PI value is 2.34 add 9.69 divided by 2. That's approximately 6. Okay, for here, aspartic acids, you have to add these two. Okay, so that's add up together is 1.88 add 3.65 divided by 2. This is approximately 2.7. So last one, you have to add this guy and that guy. Then this is 9.04 add 12.48 divided by 2. This is equals approximately 11. Okay, so this is what we find the pK value. Dr. J students, graduate students do these all the time because they have to adjust the pH value to reach the pKa. So it will cause some precipitation. Then you have a high-speed centrifuge. You could get the supernatants and also get the precipitation. Okay, so that's how we calculate that. Okay, last one. We want to talk about the protein structure. This is not difficult. Everybody knows. Number one is primary structure. So primary structure, said very simple, is amino acids sequence. Okay, amino acid sequence, what it looks like. Let's say I have a CNH, CR1H, COOH. Then you plus the second one is NH2, CR2H, and COOH. If it's combined, what happens? We'll lose water. So we'll become NH2, CR1H, C, then goes NH, goes CR2H, COOH. Here, you always should remember, this is called peptide bonds. Is that right? Peptide bond. And this is called N-terminal. And the right side is called C-terminal. And the number of the amino acids, let's say, is N. And the peptide bonds is always N minus 1. That's the basic knowledge. Secondary structure. What are the secondary structure we call? Localized, regular. I can say regular structure, localized regular structure. What are the three major examples? Number one, alpha helix. What it looks like? Go to this. Okay, one turn, 3.6 amino acid base, and 0.54 nanometer. There is a story behind it. Do you know who found this? Linus Pauling. What's the story behind it? Alpha helix very similar to this guy. Did you find a similarity to this? A complementary with T, C complementary with G. Is that similar? This is DNA. Is that right? DNA double helix. Back in 1950s, Linus Pauling and Crick and Watson, they are the competitive group to find the DNA structure. And I want to tell you, the story tells us Linus Pauling is about 5 to 10 years earlier. He already knows the DNA structure most likely will be a double helix, will be a helix, because he thinks it's very similar to protein. But he didn't touch down the base, did the final thing, because Crick and Watson, they go to Cambridge and find who? Rosalind Franklin. And Rosalind Franklin showed him X-ray deficient photographer and find the double helix. But that's not important. Everybody at that stage knows. They both, Crick and Watson and Linus Pauling, both they know it could be a double helix, 90%. What they are missing here? Crick and Watson very lucky. Shagraf rules. They have a lunch with Shagraf, and Shagraf tell him the ratio of A and T is 1:1, C and G is 1:1. That's a final determine. And the history, the storyteller, the Shagraf is very regret to tell us, to meet with Crick and Watson, tell them the story, because that's a final touchdown. When they finally determine the DNA, A and T and C and G, double helix is based on Shagraf rules. All the biochemistry textbook, it does not matter in the United States, in China, they always say Rosalind Franklin have a major contribution, show them the X-ray photographer. Kind of the reason because Rosalind Franklin had a cancer by the time. She died after 2 years. Otherwise, Rosalind Franklin will also award the Nobel Prize. So that's a story behind it. Linus Pauling is very close to get it. But luckily, Shagraf had a Nobel Prize later on. Crick and Watson has a Nobel Prize, and he had 2 Nobel Prizes. So from the honors level, they are all equal. Okay. That's the story behind the alpha helix. Second one, beta sheet. That is what it looks like. Just you know, like this, like this, like that, like this, beta sheet. Okay. Number 3, random coil, like this. Okay, that is secondary structure. What is third structure? Or tertiary structure. Tertiary structure, we usually say it is 3D configuration of alpha helix, beta sheet, or random coil, folded, or composed in a globular status. And most likely they will connected with sulfide double bonds or disulfide double bonds. So what it looks like? It in a circle. So you have a alpha helix there. So you have a random coil right here. So you also have these beta sheets there, and then they connected using disulfide bond. Okay, the last one, coronary structure. What is the coronary structure? Assembly of polypeptides using non-covalent nor disulfide bonds. These polypeptides referred as subunit. A good example, hemoglobin has A, B, C, D, 4 subunits connected. Okay, so that is a basic knowledge what we here talk about amino acids and the protein. All these things is really the background. So when we talk about the muscle foods, talk about the Maillard reaction, then let you review all these basic biochemistry information and the chemical information. And this will be included in the exam 1 next week. Then after this, we'll do the exam 2. But we don't have an exam 2. Exam 2 will be you take home, which means imagine you are instructor, you're going to generate 20 questions. What are you going to do? So that will be an open book take home questions. Okay?